this circuit, this pesky little circuit, is surprisingly hard for people to solve. So I'll solve it. I'll solve it a couple of ways to give you a chance to think about it. I'd like to know the Thevenin circuit between each node. So between 1 and 2, 2 and 3, and 1 and 3. And I don't really know why it's so surprisingly hard for people to solve and to get right. I think it just looks too simple, and people look at it and think they know what's going on. So first, we'll do from 1 to 2. And I'll redraw it without pin 3. So it's not needed, right? So I'll just redraw it, and I'll slide resistor R2 down just a little ways. So I'm just going to slide it down the same wire. And so we've got pin 1 and pin 2, and we've got R1 and R2. I just moved it. All I did was move it from this location over here, right? I just slid it down over to there. I didn't really change the location. In the first position, R2 is directly connected by a wire to the minus pin of this 1.5 volt source. It's connected to pin 3, but I deleted that. So I haven't changed it. R2 is still connected to the minus pin of that 1.5 volt source. It's still precisely the same situation. Got 1.5 volts there. But hopefully with it there now, you could realize it's a little easier to solve. So if we want to find the resistance, looking into pin 1, between pin 1 and 2, I'll call it Rn equals, well, open up the voltage source. So I've drawn it as a battery here, but whatever it is, we'll open it up. So I'll just draw the circuit again, and I'll slide R2 even farther up. So we've got R2, which is 1K, and R1, which is 1K. We've got pin 1 and pin 2, and that's where the opened up 1.5 volt source is. It's a short, right? So now when you draw it this way, it's easy to see that our in is just equal to the equivalent resistance of these two resistors, which is the two resistors in parallel. And that equals 1 over 1K plus 1 over 1K, the inverse of that. And then since they're the same, it's just 500 ohms. Okay, so that's easy. It's 500 ohms. Got that. Looking to pins 2 and 3, looking right in there between pins 1 and 2, we get 500 ohms. Looking at those, you may or may not feel like R1 and R2 are in parallel when you look at this drawing right here. But if we're ignoring pin 3, that is the case. So those extraneous marks. I wish I could make it not draw those in. Now we need to find V2. It's a divider, but maybe it looks upside down. So I'll redraw it one more time. So, oops. I told you should know, the divider equation, just instantly be able to do it. And you really should. You don't have to solve things that way, but it is sometimes just a really easy way to do it. So if I redraw it again, just leaving off pin 3. Pin 3 was down at the bottom there. But we've got pin 2 and pin 1. Got 1K and 1K and 1.5 volts. And the divider, geez, I didn't want to do that. It's impossible to just erase that one line. Okay, so we got 1K. The divider equation, looking into that, right into here, it's the same, but you might used to be usually finding this voltage by divider from 2 to 1, but we're trying to find it from 1 to 2. So it's the normal divider equation, but maybe it's going to look a little different because we need to kind of look at it from the top, not the bottom. And the divider equation works perfectly fine either way. So voltage 1 to 2, let's write it like that, voltage 1 to 2 is equal to, this is R1 and R2, is equal to R1 over R1 plus R2 times the 1.5 volts. And of course, that's just 1,000 over 1,000 plus 1,000 times 1.5, which is 1/2 of 1.5 or 0.75 volts. So you should be able to just look at it and basically instantly write the divider equation. and with that, we know this voltage is 500 ohms and we got a 0.75 volt. So we could draw the Thevenin equivalent equation between 1 and 2. 1 and 2. We've got 0.75 volts and we've got 500 ohms. That's between 1 and 2. Now for 2 and 3, it's the same as 1 and 2. It's identical. If you really felt like drawing it all out again, more power to you, you can. But it's not necessary. But it's only in this case. Why? Well, with just 2 resistors, the equivalent resistance will be the same if R1 doesn't equal R2, but that voltage will be different if we use R1 is not equal to R2. So you would just have different values to put into the divider, which I don't think I really need to demonstrate to you. Just you'd have different values to put in there if R1 and R2 are not the same. But the analysis would still basically be exactly the same. So that's one way of solving it. Now, how about 1 and 3? Okay, so between nodes 1 and 3. Come on. Okay, we're going to go to that. We'll pick, go back to black. So now 1 to 3. Well, so we want to redraw it and leave off node 2. So we've got 1.5 volts. We've got R1 equals 1K, R2 equals 1K. Got node 1 and node 3. All right, and we want to find Rin, 1 to 3. Want to find those two. Well, okay. We want to short out to find Rin again. Short this voltage source out. Open it up, short it. So I'll redraw it without that source. Let's go back to black. So I'll draw it without the source. You really have the source in there. Change colors again. So it's right in there, that 1.5 volt source. It's shorted. Good. Nodes 1 and node 3, R1 and R2. Node 2 was in between there, but we don't need it anymore. I drew it without it. And so if we look for Rin now, Rin is the resistance we see looking in. Well, we've got these two resistors here in series. So there's 2K of resistance in series here. But if we look over here, we have 0 ohms here because of this short right there. Oh, that's really important. You can't ignore that short. It's the whole kit caboodle. So with that, Rin is equal to 0. There's 0 ohms. It's 0 ohms. It's a short. And if that's the case, well, it's as if R1 and R2 don't exist. And so the voltage between them, the circuit, is just this 1.5 volt source. It's as if R1 equals R2 equals an open. They just don't exist. They don't matter. It doesn't matter what they are. They're just not there because we've got a 1.5 volt source that you can see right here. Up at this point, you can see it. This 1.5 is appearing at these nodes 1 and 3, but people somehow don't want to believe that that's all it is, that it's that simple. It really is that simple. So don't be fooled by these evil looking things. They really are sometimes easier than you want to believe. Now, we could also do this with Thevenin and Norton conversions, and maybe it could be easier. I think it might be easier and intuitive. Now, one thing you need to remember for a source, and I kind of already alluded to this, is that you can put the resistor on either side of the source. So if we have a current source, we could put the resistor here. Oops. let's draw it as a full-blown resistor here. We could put that Norton resistor there, or we could put it over here. It's perfectly valid either place. It can be either side because that top bar, this bar here, is shorting this whole area, and this bar is shorting this whole area. So the connection here is the same as here, and likewise the connection here and here and here are all equivalent. They're all the same. So we can put those resistors either side. It's still valid. We might usually put it over here, but it does not need to be there. And likewise, for a Thevenin, we can put the resistor above or below. So not drawing a very good dot there. I switched colors. It did the same thing, the same sum total resistance, the same effect is going to occur either way that we put that. So it's just important. So I already moved that resistance around. So I'll just draw it again, but I'll draw it out again. So we originally have this circuit here that looks like this. 1, 2. 1, 2, 3. That's the original circuit. And I can draw it around. I can draw that resistor so it's like that. So at first we're going 1 to 2, 1 to 2. And we've got R2 and R1 and 1.5 volts. It's the same circuit. And maybe that makes you nervous because it's on the bottom, like I said, so we can certainly put it on top. It will still be the same equivalent Thevenin circuit. And hopefully now it looks exceedingly familiar. Remember, that's R1, this is R2, and this is 1.5 volts. I know it's R2 because R2 is the resistor that I slid around, right? I slid R2 around to here, and once I had it here, I slid it over to the other side up to here, and then I have it up here. So that's R2. It's not R1. Don't get confused about that. But once you have it in this position, then hopefully it feels like a straightforward thing to do when you've got a Thevenin and a Norton, and you're going, well, I don't know what to do here. Take the Thevenin, make it a Norton. So we have 1.5 divided by 1K. That's 1.5 milliamps going into a resistor. And then we have a couple of resistors in parallel. So that's the Thevenin equivalent of this. That is the same as this, but then we need to add that other resistor right there. So let me draw that in. We got 1K And then we've got 1K, R2, R1, sorry, R2 and R1 actually. Well, it's no longer R1 and R2. This resistor on the right is technically still R1, but it's just, we'll just leave it as 1K. Got node 1 and node 2 there. Got these in parallel. So we can simplify this as the equivalent resistance. Our equivalent is obviously 1K plus 1 over 1K. That resistance that's in there with that Norton source. And then if we were supposed to find that Norton circuit, and we just got to go back and do it with do the Norton to Thevenin conversion. So we got 0.0015 amps times 500 ohms, be 0.75 volts. So voltage source, and 500 ohms would be the resistance. So from 1 to 2, that's the Thevenin circuit. And 2 to 3 is still the same. Although, of course, as before, if you had a different value of R1 and R2, then you would need to draw those in. But it's all still the same. And the 1.5 volt still appears across the up between 1 and 3, and so that's all you get. So I hope that maybe makes it a little easier, and or at least gives you a consistent way to solve it and clears up some of that mystery. It's really not a difficult circuit, but it's so easy to goof up. So I'll make some practice after that. So after this, so you can try some practice to try and make sure that you get this right.